Уважаемые коллеги, у нас уже началась трансляция на YouTube, поэтому скоро мы начинаем. Будет проведена запись вебинара. Юрий Владимирович, вы разрешите сделать несколько организационных объявлений до того, как будет начата запись вебинара?
Конечно,
Уважаемые
конечно.
коллеги, я рада вас всех приветствовать на нашем мероприятии. Несколько организационных объявлений о том, что необходимо сделать для того, чтобы мы с вами все вместе эффективно поучаствовали в нашем вебинаре. Пожалуйста, выберите язык, на котором вы хотите слушать наш вебинар. Если вам нужен язык русский, то поставьте, пожалуйста, язык русский. Если нужен английский, соответственно, английский. Мы анонсировали, что вы сможете задавать вопросы на вебинаре. Для этого вы можете воспользоваться либо функцией «Вопросы-ответы» на панели инструментов, либо вы можете задавать вопросы устно, но для этого вам нужно поднять руку. После того, как модератор семинара предоставит вам слово, вы будете переведены в активный режим и сможете задать свой вопрос. После того, как дискуссия по вашему вопросу будет закончена, мы, как организаторы, переведем вас обратно в режим участник. Всего в нашем вебинаре зарегистрировалось на участие свыше 80 человек. У нас некоторые институты подключились коллективно. Вот вы, например, видите окно Белгим. Мы предполагаем, что сейчас к нам присоединится президент КАМИТ и поприветствует вас от своего имени. Также мы знаем, что подключались коллективно специалисты Укрметра Тест-стандарта и Азербайджанского института метрологии, поэтому мы чуть попозже анонсируем, какое общее количество участников у нас сегодня будет в семинаре. Будет вестись запись нашего вебинара, которая также потом будет доступна. И, наверное, это все организационные объявления, которые я хотела сделать. И я передаю слово Юрию Владимировичу Кузьменко, исполняющему обязанности председателя ТК-2 «Законодательная метрология», для того, чтобы официально начать наш вебинар и продолжить нашу с вами совместную работу. Я включаю запись и тогда мы сможем продолжить. Спасибо.
Здравствуйте, коллеги. Я искренне польщен тем, какое внимание к этому семинару на сегодняшний день, судя по участию, по заявкам на это участие выказано. Мы надеемся, что это всем пойдет на пользу. Конечно, мы должны отметить, что жизнь в режиме пандемии внесла большую корректировку в наши отношения. Конечно, мы должны беречь свое здоровье, свои жизни. Благо, мы живем в век технологий, которые нас могут сблизить, и мы можем на сегодняшний день себе позволить в электронном, виртуальном поле встречаться, обмениваться необходимой для специалистов, для научных сотрудников, для метрологов всех сфер деятельности информацией. Конечно же, мы воспринимаем этот вебинар исключительно как глоток свежего воздуха. Мы можем себе позволить пообщаться на этой площадке, и мы должны понимать, что не для всех просто, допустим, задавать вопросы не очно, не в личном общении. Тем не менее, я прошу всех, у кого возникают какие-то недопонимания и так далее, но и с другой стороны мы понимаем, что время не так широко для нас, для того, чтобы мы могли обсудить, ну, буквально каждый глубокий вопрос. Мы записываем, как правильно сказала Надежда, этот семинар и транслируем его в YouTube. Мы говорим о законодательной метрологии, помню о том, что у многих бытует мнение, что законодательная метрология – это прежде всего свод правил, нормативно-правовых актов. Мы все вместе прекрасно понимаем, что принятие любого решения, особенно в оценке соответствия, невозможно без глубокого знания физики процесса измерения и без надежной математической модели. Вот благодаря нашему коллеге, нашему другу Петеру Ульбигу, мы на сегодняшний день, который глубоко вник в документ Международной организации законодательной метрологии, мы на сегодняшний день можем почерпнуть новые знания и более глубоко разобраться в подходе, математическом подходе, который подкрепит надежное решение в законодательной метрологии в такой тонкой и непростой области, которая является оценка соответствия, с помощью прекрасного гайда, базированного на хорошей математической теории, я имею в виду прежде всего на теории неопределенности. Поэтому я искренне верю в то, что наш семинар, наш вебинар будет крайне полезным, и мы почерпнем новые знания, и эти знания позволят нам улучшить наши инфраструктуры качества в каждом конкретном государстве и в целом для блага наших экономик и наращивания наших возможностей и способностей. Огромное спасибо. Я передам слово Наде от имени секретариата, если у нас еще есть какие-то объявления. И, в принципе, я так думаю, что мы могли бы уже начинать.
Спасибо, Юрий. Ну, вроде как никаких больше технических вопросов нет. Мы не видим в чате никаких технических вопросов со стороны участников. Я надеюсь, что все подключили нужный язык, поэтому мы можем, наверное, начинать и дальше работать по программе вебинара.
Поэтому я, с вашего разрешения, передаю слово нашему лектору Петеру Ульбигу, и мы приступаем к внимательному разбору всего сложного и непростого к пониманию документа. Спасибо, Петер, пожалуйста.
Okay. Hello, everybody around the world, whoever listens to this or watches this seminar from someplace in the world. I'm working from home those days, and for this reason, you can see I'm just in my private home. I'm happy that so many people attend the seminar today. I didn't expect so many people, but I'm happy about that. And I will do my very best that everybody can really take some knowledge from today and also can apply some parts of or some the guide, let's say. I would like to share my screen now that you can really see what I'm talking about. I think hopefully it will work. So can you see the, one moment. Can you see the screen in the presentation mode? I just can't hear anything. Pardon? Yes, it's fine. Is it okay? So Nadia, could you give me a sign whether it's okay?
Yes, Peter, we can hear you and so
Да, Питер, видно, но не полностью.
Okay, okay, then I like to start with the seminar. So yeah, so that's the outline for today. First of all, I would like to give you some, let's say, general introduction into the topic before I will give you the introduction into the OML G19, the guide number 19, dealing with the role of measurement uncertainty in conformity assessment in legal metrology. However, today's seminar, I would like to chance also to go even beyond the guide and to give you some help that you really can apply this guide. And so I will also talk a little bit about how to calculate measurement uncertainties. And also I would like to give you some information about useful software to calculate measurement uncertainties, because this is necessary really that you can apply the guide. Before we start, of course, you can get this presentation after the seminar. It's about 150 pages, so you have to expect quite a lot today. And I would like also to share some additional documents in this context, which I find very useful. And so I will also send them to COMET Secretariat, that you can also download them from the comet.net website. But of course, you may take your own notes, feel free. And we will also collect some questions if there are any, and I would be happy to answer them. So there's a huge interest in this seminar. As I mentioned, we expected about 15 participants from the COMET TC2, the Technical Committee for Legal Metrology, but now there are almost 100 participants taking part in the seminar. And I think the good thing is, if you look at Corona and the pandemic, now, according to the technology we use, now many more participants can take part in the seminar as we already, intended in the beginning. So I think it's a good start. I was wondering a little bit about this high interest. And I asked myself, why is there such a high interest? And do you think that there is some magic in there in this topic? But to be honest, I have to tell you, I will disappoint you maybe, because there is no magic. It is only some math, some mathematics. And also we need to apply some software, some tools, and then it's relatively easy. Another reason for this high interest could be that you ask yourself, am I doing anything wrong? Because if we deal with conformity assessment, with inspection, with verification, with testing, then usually we apply the, let's say, classical approach. And we know that this could be wrong in some cases, because there is some uncertainty behind. And I would like to speak today especially about the risks we have in conformity assessment. So what is the reason for this seminar? There was interest of the members of the COMET TC2 Legal Metrology, because we deal with conformity assessment in legal metrology. It means type approval, testing, verification, market surveillance. And we always asked ourselves the question, is the conformity of a product given to legislation? So does a product fulfill the requirements by law? And therefore, we try to test the instrument, and we have a look whether all the requirements are fulfilled. So what do we do normally? The classical approach is to check whether a measured value, an indicated value, is within the maximum permissible errors given by legislation. And I made a short sketch, a simple sketch. You can see here some measurement scale. Maybe it could be some voltage or mass or whatever. And usually we apply a measurement standard. That's the value you can see here. And usually we have a minus tolerance, which means the maximum permissible error to the left, and also the positive deviation, the positive maximum permissible error. So that's the range of values or the interval where all the indicated measured values of the device under test should be. And for example, in this case, maybe the indication maybe is here, the indicated measured value is here. And so we say, oh, everything is well, because the indication of the measuring instrument is just within this interval. But is this really true? We know by principle that this could be wrong in some cases. And here exactly the OML G19 comes in. We know we need to deal with measurement uncertainties, but in today's seminar, the knowledge within the auditorium about measurement uncertainties might be totally different. So, because most of the colleagues in legal metrology don't deal with measurement uncertainties on a daily basis. And so the intention is to hold this seminar on a more basic level. So, and as this is a YouTube stream, respectively a Zoom conference, so whenever it is too boring for you, of course, you can do something else. You can just take a coffee or whatever. So feel free really to take the knowledge from today's seminar, what you like to have. So what could you take home in quotation marks after this seminar? You should have an overview about the OML guide number 19. You should have some basic information about measurement uncertainties, some information about calculating the risk to make a wrong decision in conformity assessment. And you should have also some information about useful commercial and also free software to calculate measurement uncertainties, that you are really able to apply the guide. So this is the guide OML G19, the edition from 2017. And I have to say, I'm really grateful to all the colleagues in the world who contributed in the elaboration of this guide, because it's really a very good guide. I was really surprised when I went through how good this guide is and how useful it is. And hopefully after the seminar, you are of the same opinion. So this guide is the responsibility of the OML Technical Committee number 3, the subcommittee number 5. It was developed by the project group number 2. They got the task for a guide expression of uncertainty in measurement and legal metrology applications. And finally, they developed this guide number 19. And also, I think they will maintain it. And from time to time, I guess there will be a little revision. So if we have a look at this technical committee, the subcommittee number 5, the secretariat is held by Dr. Charles Ehrlich from the US. Last year, I invited him to take part in today's meeting and to present all the contents of the guide. Unfortunately, he was not able to take part today. But if we have a look, especially to the CUMET countries, which are also represented in this subcommittee, it's Bulgaria, Cuba, Romania, Turkey, Slovakia, and also Germany. So some of our CUMET member countries also take part in this work, which I find very useful. So now let's start with a guide intensively. And I would like to start with the chapter number 1, the scope and objectives. And there it is written that it is assumed that the reader has at least a general familiarity with the concepts presented in the guide to the expression of uncertainty in measurement, which is called the GUM, the abbreviation is the GUM, and possibly also with the concepts in its supplements. So I guess most of you have some idea about the calculation of uncertainties in measurement. But today I will go through this guide step by step, and I will explain a lot, I guess. It is also written there that it is anticipated that this guide will eventually become an OML document, so a little bit more than just a guide. Because the idea is that all those contents of the guide number 19 should be somehow included in other OML recommendations and also documents. However, that's not the case right now, but I guess in the future, so the project groups of the OML developing recommendations, they should consider the contents of this guide and how they could be incorporated into the recommendations and documents. So that's the future. The main objective of this guide is to provide guidance how to take measurement uncertainty into account in conformity assessment and legal metrology. And as I mentioned in the beginning, this could be testing of an instrument, verification, market surveillance activities, inspection, however you call it. So whenever you prove whether an instrument fulfill the requirements. So an entity, a product, it's just to determine whether an entity is, in our case, a product, meets relevant standards or fulfills specified requirements. And particular focus is on conformity assessment of measuring instruments or systems during the testing or verification of the measuring instruments as a basis for making pass or fail decisions in legal metrology. And this guide is not intended for pre-packages. I think that's important to note. So the proposals include providing and referencing information on how to assess the possible risks of erroneous conformity decisions. Because we have such risks, we cannot avoid them. And therefore, it's good to know how large the risks is. Because it's really important, because it can lead to incorrect estimates of the consequences. And for example, such as failing a conforming entity, a conforming product, or passing a non-conforming product. And I'm sure that nobody would like to have to make such a wrong decision, and therefore it's good to know the risk we have. So in the chapter 2, terms and definitions, there is made reference to, in principle, 3 documents, the most important documents we have in metrology. It's the vocabulary, the international vocabulary in metrology, the VIM. Then we have also the international vocabulary of terms in legal metrology, the VIML. And as already mentioned, we have this the guide, or the GAM, the evaluation of measurement data, the so-called guide to the expression of uncertainty in measurement. And I would like to highlight that those 3 documents can be downloaded free of charge from the OIML webpage. And if you don't have them already, those documents, then it's a good idea really to go to the OIM webpage, to the documents section, and to download these documents. So now we really start with a topic. And in the chapter number 3, which is called Introduction, there's already such a picture where you can see such a so-called distribution function, which is a probability density function, it is called. For this reason, you can see here on the y-axis probability density. It's written here. And here on the x-axis, you can see some quantity. For example, in this case, it's a power measured in watts. And you can see here, this is the measured value, but this is the most probable value you could measure. But if you do measurements in case of repeated measurements, it might happen that you also measure maybe this value or that value, or even maybe such a value. So it depends. And usually if you take 100 or 1,000 or even more measurements, then usually you get such a result, that you never exactly measure the same value, but that you measure somehow distributed values. And in this context, you can see also here the standard measurement uncertainty, in this case of 0.8%, which means that about 68% of all the measured values are within this range. So within surrounding this mean value. And if you expand the measurement uncertainty by a factor of almost 2, then you have about or a little bit more than 95% of all the measurements can be found just in this range. So resulting in this curve. So that's just the basic understanding of measurements, that we always get some distribution. The concept of measurement uncertainty is frequently used if we calibrate some instruments. And here in this diagram, you can see again this curve. I expanded it a little bit. And you can see also some little red curve, also some kind of distribution function here. And this means this is the uncertainty of the measurement standard we use for calibration or testing or verification or whatsoever, which gives the traceability to our measurements. And the meaning of this picture is that whenever we measure something against a measurement standard, then the uncertainty of the measurement standard always is some part of the overall uncertainty. So this curve results also from this part. Of course, there are many other contributions, but it is essential, important to note that the uncertainty of the measurement standard is also a part of this overall curve. But it is important to note that the probability, because it is a probability density function, this curve never reaches 0. It goes down, it is an exponential curve. And I guess you know exponential functions. It looks like it would reach 0, but if you have a closer look, then it's never 0. So this curve goes down and down, but it never reaches 0. So it is the y-axis, and the value of 0. And so it is important because finally we need to calculate the area under this curve, and we have to be aware that there's always some area also if we go to infinity or minus infinity, there's always something gonna happen here, and there's always some area below this curve. It never reaches 0. So what we do in conformity assessment, let's say in verification or testing or conformity assessment, usually we apply a measurement standard which has a certain value, usually a certified value. And then we check an instrument, the indication of an instrument. And then we apply maximum permissible errors given by law, given by legislation. So MPE, the abbreviation, means maximum permissible error. So, and we check the classical approach whether the mean value, the indicated value, is just within this interval between minus MPE and plus MPE. But questions arise. Is a measuring instrument under test really conform if it shows such a behavior? What situation is acceptable? What is non-acceptable? Because sometimes the indicated value is very close to the limits, to the maximum permissible errors. Is it still acceptable? And what is the risk for passing the test when the instrument in principle is non-conform? Or vice versa? What is the risk for failing the test also when the instrument is conform? So there is a risk in both directions. So you always have to take some measures or some calculations to calculate this risk and then to decide whether you accept an instrument or not. And I will explain this in more detail now. So let's take some examples. First example. So this is maybe the best way we can have. So we apply a measurement standard and we measure some values, and the result is this, that the mean value of this curve, the highest point of this curve, is really exactly in the middle of this interval. It's really now symmetrically here in this interval, the curve. And so we can be very happy, because I think you would agree that we have a very small risk that the instrument under test is really non-conform. We expect it is conform. And even if the curve goes down here and also some little part is outside the maximum permissible errors on the right and the left, we would say this instrument is conform. So these areas are very, very small under the curve. The highest amount of the area is just within the interval, and so that's fine to us. If the curve or the measured values move to the side a little bit, then of course I think you would agree then that we get somehow a higher risk that the instrument is non-conform. And you can see also here on the left that this area, which is marked blue here outside, that this area increases. So this is we get some idea also from this area here that we get some higher risk. Of course, on this side, the area is extremely small, and maybe we can neglect this more or less, but this area really here has increased. If we move again to this situation, where the measured values or the highest, the mean value of all the measurements is exactly here on this edge where the maximum permissible error is, the negative tolerance, then we have this very large area here outside and only some part inside this interval. And then the question is really, does such an instrument fulfill the requirements? Is it conform or is it non-conform? And in such a case, we reach a relatively big risk, which is approximately 50%. And you have to, well, I would like to mention that on one hand, this area is outside our interval, and also this area in principle is outside. And even if this is very, very small, there is some area to the left and to the right, which also gives us some idea about the risk. And if we move again further, if the measured quantity value is the mean value, the highest point is really outside the interval, then we have a very big risk that the instrument is really non-conform. And I think you would say, okay, in such a case, it's clear to me, the instrument is not conform, but what if you measure, for example, such a value or such a value, which are within the interval of the maximum permissible errors? And so there is still some probability that the instrument is conform. However, we have a very big risk, which is larger than 50%, that the instrument is non-conform. So you can see from this example that it's not always so easy to decide whether the instrument is really conform or not conform. And so we have to go a little bit deeper into this. So what I would like to highlight, the area under the curve, under this probability density curve, is somehow proportional to the risk. And for this reason, our intention will be to calculate the shape of this curve, that we get the parameters of this curve. And then we are finally able to calculate the area which is outside the maximum permissible errors and also the area which is inside, which is under the curve and inside this interval. So from that, we can define the risk, whether an instrument is conform or non-conform. And I would like to start with the risk of an instrument which we consider to be conform being non-conform. And as I mentioned already, the areas here under this curve, so we have to calculate this area outside, we have to calculate also this area outside, and we have to calculate this whole white area here under the curve, which is inside this interval. And the risk of such an instrument, which is considered to be conform, that it is really non-conform, is given by the ratio of the areas. So we have to calculate the outer area, and in the denominator here we have the outer area and the inner area. Or in simple words, the risk is given by the outside area in respect to the total area under the curve. I would like also to mention, it's not just only the risk of a conform instrument being non-conform, it's also considered to be the risk of a conform instrument failing the test. So it means in principle the same at the same time. So if this area outside increases, if the whole curve is moved to the left, then the risk increases that an instrument, a conform instrument, fails the test or is really non-conform. On the other hand, I mentioned the second risk, the risk of an instrument which is considered to be non-conform, the risk that it is conform. So it is vice versa. So in this case, the curve or the maximum should be outside the maximum permissible errors, but there's still some area inside the interval. And so we have to calculate the risk as the inner area in respect to the total area. So this is also the risk that a non-conform instrument, which we consider is non-conform, that it passes the test. Because if you assume that you measure somewhere a value here inside the maximum permissible error, then you would say, oh, it's fine, it's conform, but in principle it is non-conform. So this is the risk of an instrument which we consider to be non-conform, that it is conform. So we have those two different risks, and in both cases it is related to the areas under the curve inside and outside the interval given by the maximum permissible errors. And last week, I got a note or some information from Harry Stolz, who also attends the seminar. Hi, Harry. And he gave me information about the requirement in the ISO IEC 17025, the standard from 2017, because there is a new, or let's say relatively new requirement, which was included concerning decision rules in test reports. And there it is written in this chapter 7861, when a statement of conformity to a specification or standard is provided, the laboratory shall document the decision rule employed, taking into account the level of risk, such as false accept and false reject as statistical assumptions associated with the decision rule employed and apply the decision rule. So this is exactly the key. You have to take care on those risks. You have to specify the risk if you apply the ISO IEC 17025, if you do some testing according to the standard, then you have to do this. You have to calculate the risk. And that's the reason why it is also very important that you are able to apply this guide number 19 of the OIML. So another very practical question, maybe also which came to your mind. If we have always some measurement uncertainty as part of the overall uncertainty of the measurement, then the question is, how big should the measurement uncertainty of your measurement standard, for example, used for verification, be compared with this maximum permissible error? And maybe you know that some people say, oh, the uncertainty of the standard, of the measurement standard, should be 1/3 or 1/4 or 1/5 or 1/10 or whatever. So there is some people saying, oh, there should be some values, should be some fraction of the maximum permissible error. And the nice thing is that if we apply this guide number 19, we are able to calculate the risk, and also the correspondingly the fraction, how small the measurement uncertainty of the measurement standard should be. And I will come back to this topic a little bit later. So the uncertainty of the measurement standard always has also an impact on the risk of a possible wrong decision. But we should be aware of this. As I said, we will come back to this topic a little bit later. So what is also important to mention, the whole concept of measurement uncertainty can be described as a measure of how well the true value in quotation marks, of the measurement is believed to be known. If we consider this diagram, this sketch here, you don't find any true value in this diagram because nobody knows where the true value is. It is not possible to know how well the true value of the measurement is known. And so if we take this concept of measurement uncertainties, we always have to believe, we have to have a belief that our measurement is somehow close to the true value, but we will never know what the true value really is. And that makes decisions difficult. When making decisions in legal metrology about whether a measuring system is performing according to specified requirements, it becomes necessary to make such decisions on a probabilistic basis. There's always some probability that it is right. It could be wrong, that your decision is wrong, could be. And testing or verifying an instrument in this context means that a decision is being made about whether the measuring system under test is providing indicated values of a quantity being measured that are believed to be close enough to the true value as determined by using measurement standards for the regulatory purpose at hand. So I think that's very important that we are aware. We are talking about probabilities. We never can be sure. There's always some risk to be wrong, but we have some chances to reduce this risk as much as possible. So in the guide number 19 of the OIML, there's also a very useful Annex A, which also deals with the terms, with the term error on one hand, and also measurement uncertainty on the other hand. What the idea is, if we do some testing or verification or whatever, is to determine the degree of belief, or we can call it the level of confidence, that the true value or the error of indication lies within the maximum permissible errors when taking measurement uncertainties into account. So it just simply means we have the maximum permissible errors given by law, we apply our measurement standards, and we develop some belief whether the measured values are inside this interval and whether the instrument is conform. So there's a frequent question from colleagues around the world concerning this topic. How can measurement error and measurement uncertainty can coexist when considering measurement in the context of conformity assessment? So it means we are dealing with conformity assessment. Our measurement standard has a specified measurement uncertainty, and we apply this standard to measure some error, or we determine some error. And does this really work? Is it really right to do this? And I will also say some words about this, because finally you will see that it really is harmonizes. It's really it is a good approach to apply a standard with some measurement uncertainties, and also to apply maximum permissible errors at the same time. And you can get really some decision. You can make a decision. So this was the first part of the introduction, and also to guide you a little bit to the topic. Now we really go into this topic, and this would be time for a little break concerning also maybe questions and remarks. And I don't know whether there are any questions or remarks right now, maybe have given by the chat function. So I ask the organizers whether they can give me some information. Whether
no, Peter, there is no questions on
okay.
chat.
I have a look to my watch. It's now 11:15. I would prefer now to have a short break of 10 minutes, because then I don't have to interrupt when we really go deep into the topic. And my proposal is that we come back at maybe 11. I think 11 is fine. And if you have some questions already, then please write them into the chat. And then I will take also the time to answer those questions, if there are any so far. So we meet again at 11.
Ни у кого нет возражений на этот счет? Надя?
Нет возражений, поэтому, наверное, имеет смысл так и поступить, чтобы Питер потом смог продолжить свою новую презентацию. Тогда я приостанавливаю запись.
Да, дорогие коллеги, до 12. Встречаемся в 12.
So could you give me some signal when I should start again?
Питер, переводчики с нами. Надеюсь, участники тоже.
Okay, fine. Are there any questions collected so far? I don't hear anything right now, so I guess there are no questions. Is it right? Okay. Then I proceed with the presentation. And now I would like to go into detail a little bit more. Cursor. Here. So, okay. So the question we just had before the break was, how can measurement error on one side and measurement uncertainty on the other side coexist when considering measurement in the context of verification, or let's say conformity assessment? Conformity assessment in legal metrology typically involves comparing the measured error of indication of a measuring instrument or system to a maximum permissible error that is specified in a legal regulation. So this term, measured error of indication, this is now very important. The error of indication, or the measured error of indication, is typically calculated in legal metrology as a difference between the indicated value and a value as given by a measurement standard. And here also the measurement uncertainty comes in. Let's take a simple example. Here on the upper part of this page, you can see a standard weight. And here on this, in this sketch, you can see the possible quantity values of mass. So this is a mass scale. And here again, we have the probability density that a measured value of the mass of the standard weight corresponds to the true value of the mass of the standard weight. And here you can see now, again, a probability density function. These are the values of your standard weight, of your reference, which also has some probability density function. And in this chart, you can see also the true value of the mass, which nobody knows. But just by for this sketch, it is was just introduced here. So it exists, but unknowable in principle. What is important, that also this calibrated standard weight has some deviation, of course, or should have some deviation, should show some deviation to the so-called true value. But that's, we don't know the true value. For this reason, it's not really helpful. So what do we do if we really try to make a test of a weighing instrument, for example? You can see here there's a very simple weighing instrument, and we put a standard weight on top of this weighing instrument. And now you can see different things. On one hand, again, this is the probability density function of your standard weight. So these are the values the standard weight could have, with a mean value, with a maximum, which we call the calibrated mass of the standard weight. And here now, we have the indicated value of the mass.
Peter, I'm sorry. Can you turn on the PowerPoint presentation mode, please?
Again, is the PowerPoint presentation is gone?
Presentation mode.
Sorry, I will try.
Господа, у нас, кроме всего прочего, трудности с переводом. Мы упускаем большие части перевода.
I will try. Do you see the presentation again?
Oh, yes, yes. It's great.
Did you got me or my explanation when I described this chart?
No.
Or was I lost before? So should I restart with this page?
Да, Питер, нужно повторить.
Okay, then I will restart with this page. So the idea here is that we have a standard weight, which you can see here at the top of this slide. And you can see, again, here we have a mass scale that this mass as a standard weight itself shows some probability density function, the blue curve. Just here it, sorry, yeah. Which means if you measure your standard weight, the mass of your standard weight, it shows such a behavior with an average value, with a mean value, but of course also this standard weight has some standard measurement uncertainty. And it shows some deviation to the true value, but of course, as I mentioned, we don't know where the true value is. For this reason, this difference is not really helpful to be considered. And therefore, we do it a little bit differently. On this slide, you can see, again, the standard weight, which is put on a weighing instrument under test. So that's an instrument we test or we verify, for example. And in this case, again, we have this curve of our standard weight. We have the probability density function of our standard weight, which is, and with a mean value, the calibrated value of this mass, this weight. And in addition, of course, if we put this weight several times on the weighing instrument, of course, we get some probability density function also for the indication of the results of this weighing instrument, which is just by chance a little bit smaller here. It shows also some probability. For example, you put the instrument, the weighing standard weight 100 times on this weighing instrument, and sometimes you measure this value or that value, so you have some distribution. For example, in this case, the indicated value, the mean value, is 682.5 kg, and from the calibration certificate of our mass standard, we know it's 650. So it would show a very large difference, and usually in reality you would not see. But just as an example that you easily can follow this presentation. And therefore, the difference between the average, the mean value here, the 682.5, and the 650, this is called the measured value of error of indication. And that's why I mentioned before that this difference or this value, this number is so important. This gives us the idea really to judge whether an instrument is conform or not conform. And also we can see this is also related to measurement uncertainties. On one hand, from the standard weight, and also from the weighing procedure itself, from the weighing instrument. And if we calculate the measurement uncertainty for this whole weighing process, then we have to combine the distribution function, the density function here of the weighing procedure with the uncertainty of the standard, of the weighing, the standard weight. And this is done in the next page. Here you can see now a probability density function where those both curves were combined. It is sometimes called convolving two probability density functions. And so this is a result for this indicated value with some distribution. It also has some standard measurement uncertainty. And now in this diagram, the difference between the indicated value and the reference, the standard weight, is plotted. So here you can find now the value 0 because it's just only the difference which is plotted here in this diagram. So this, and depending where the indicated values are, where the curve is, it could be here, it could be somewhere there or there. So this varies, and therefore although the measured value of or error of indication also varies. In this case, it is just this distance here. So it is important to understand that we have this error of indication, the difference between the indication and our reference, but this follows some uncertainty rules. And here we have also some uncertainty curve, some probability density function for this testing procedure, let's say. Okay, so now we are in this diagram. We can see on one hand, we have here the maximum permissible errors given by law to the left and to the right. And here, in this case, the indicated value is within this interval. So the classical approach would mean, okay, this instrument is conform. The measured value or the measured error of indication is smaller than the maximum permissible error. However, it is somehow close to the maximum permissible error, and you can see that also some part of the curve is outside the maximum permissible error range. And that's now what we have to consider. So, in fact, it makes sense to talk about the uncertainty of a measured error of indication. We have this probability density curve. The measurement uncertainty
Peter, I'm sorry.
associated with the measurement standards, which comes just purely from our measurement standards,
Peter,
which we use
Peter,
when performing the verification
hear
test
me?
or conformity assessment,
Peter,
must be taken into account
Peter.
when making such probabilistic conformity assessment decisions.
Peter,
So it means,
do you hear me?
Yes, I hear you.
I believe we have to make a small break due
No, I can't hear
to
you.
some problems with translation. We lost the channel of translation.
The sound is gone. I can't hear you right now.
And we have to solve it due to our recording of the stream on YouTube. Please.
Can you hear me now?
Юрий, давайте
Can you
5
hear me
минут,
or
я
not?
попытаюсь с Денисом и Константином этот вопрос
Can anybody hear me?
Okay. Peter, do you hear me?
Now I hear you, Yuri. Yes.
Please let us stop for the 5 minutes. I'm sorry. Я прошу прощения перед всеми.
Денис, пожалуйста, перезвоните мне, я не могу с вами связаться.
We have to solve the problem with the translation channel for the translators.
Okay. I see.
Okay. 5 minutes, please.
Okay. Yep.
Уважаемые участники, мы просим извинить, что-то с каналом перевода, и прошу 5 минут. Мы возобновим в 12:20 наш вебинар.
Hallo Harry. Okay. Ach Gott. Ja. Ah. Da muss ich mal gucken, wie das geht. Aber danke für den Hinweis, weil das ist mal das Problem, dass man ja sich selber nicht sieht. Ja, also ich mache das jetzt mal ganz kurz. Dann kannst du mir gleich mal Rückmeldung geben, ob dann die Präsentation wieder gesehen wird. Jetzt muss ich mal gucken. So, ich habe die Präsentation eingeschaltet. Sieht man jetzt? Mist. Nee. Das ist schlecht. Okay, dann lasse ich es jetzt erstmal so, bevor ich jetzt hier irgendwas verstelle und dann geht nichts mehr. Aber teilweise ist der Ton auch einfach weg, da höre ich einfach auch gar nichts mehr. Are we able to restart now or do we have to wait?
Юрий, пока еще нужно несколько минут. Мы сейчас пытаемся решить проблему, но еще нужно несколько минут времени.
Peter, Nella says that we need a few minutes more. Did you catch?
А сейчас? А вот сейчас я появился?
Да, сейчас был слышен перевод хорошо.
Появился, да, спасибо. Мгм.
Уважаемые коллеги, переводчики переподключились. Я надеюсь, что у нас сейчас будут нормально работать канал перевода и все в порядке. Давайте попробуем.
Давайте попробуем, Петр. Мы можем пробовать продолжать.
Я прошу прощения за техническую накладку. Надеюсь, что уже проблема будет устранена со звуком.
Peter, let's continue. Let's try to continue. Do you hear me? Peter? Переподключившись, мы отключили Питера. Peter, do you hear me?
Yes, I hear you. Yes.
Oh, okay, we can go forward.
Okay, I will try. And I would like to recall maybe the main message of those slides here. I skipped back to this slide. So the whole idea behind is we forget about the true value. We don't know the true value, so we are totally not interested in the true value. We are only interested in the uncertainty of our standard weight, of our measurement standard. And in addition, we have to calculate the uncertainty of our weighing procedure, including the indication. And these two uncertainties, they together can be calculated or can be calculated to one uncertainty curve, to one probability density function. And we only consider the difference between the average, the mean value of our indicated value compared with zero, with our reference, with the standard weight. So here's the position of our standard weight, and we only consider the difference, which is described here, and we call this the measured value of error of indication, or in brief, the measured error of indication. So finally, we need to calculate this uncertainty curve. And from this uncertainty curve, you can see there's still some area inside the maximum permissible error interval, and some area is outside. And from that, we really can calculate the risk of a conform product being non-conform, or a non-conform instrument being conform. And that's what I want to show you now in the next slides. So it is important to know we do probabilistic conformity assessment decisions, and we have to take into account the standard measurement uncertainty of the error of indication, this difference. Okay, now let's proceed. So we always take the difference between the indicated value of the measuring instrument. In this case, the mean value would be 682.5 kg. This is the indicated value. And we subtract the weight or the value of our reference. For example, from the calibration certificate, we can see 650 kg. That's what we always do. We build such a difference, and then we decide, is it conform or not? In this case, the error is just here. If we use the classical approach, we are only interested in this number. We are not interested in uncertainties. We have this conformance zone between the maximum permissible errors. The error of indication is within this area, this range. And for this reason, the instrument passes, because this value is not here in the non-conformance zone on this side or on that side. It is just in this green conformance zone. So that's the classical approach. That's fine. And that's what we typically do. But as I mentioned, now the measurement uncertainties come in. So in this slide, you can see when we want to describe the measurement uncertainties, we always need a model. We need to describe our target quantity as a function of all the quantities which are relevant, the input quantities. And if we consider such a standard weight, then of course we have to take into consideration the buoyancy effects, maybe the air temperature or the ambient temperature, the ambient pressure during the calibration of the weight. all those quantities have some impact on the uncertainty of this standard weight. And for this reason, we are not able to definitively state that a measuring instrument meets specified maximum permissible error requirements and so passes a particularly conformity test. Only we can specify a degree of belief or probability expressed as a level of confidence that the measuring instrument conforms for each MPE requirement. So it is some kind of belief. That's what I wanted to express. So in the chapter 5 of this guide, now it is said that we should concentrate, we should make use of the measurement uncertainty for the purposes of making conformity decisions, especially when we are doing measurements or testing in a laboratory environment. Then it makes sense to calculate always uncertainties and then to decide, then to make a decision. The clause 6 of the chapter 6 of this guide deals with measurements performed outside a laboratory environment. For example, if we do some verification outside, and there it is mentioned that there are so many typical cases where you need to do such calculations only once, and then you take all those experiences, knowledge, and then you do the verification or the testing, and you don't need to calculate again and again for every single measurement, the measurement uncertainty, because you can then finally rely on your experience. But I will explain now the chapter 5, how really to go step by step through this approach and to take measurement uncertainties into account. So I also like to mention that the ISO IEC 17025 states that testing laboratories shall have and shall apply procedures for estimating the uncertainty of measurement. And when estimating the uncertainty of measurement, all uncertainty components which are of importance in the given situation shall be taken into account using appropriate methods of analysis. So we have to think about all those uncertainty components which are relevant for our testing procedure. For example, let's take the testing of balances. And here on the left side, you can see there's a balance which has a resolution of 0.01 kilogram. So it's not a very high resolution here. On the other side, you can see here a balance which has some more digits behind the dot, so which has a much higher resolution. And what you can expect is that when you have two balances with a different resolution, and you use the same measurement standard, so you put the same weight on those balances, finally, you will get different uncertainties. You will get different measurement uncertainties because the resolution is different, and it could be that on the right side, this balance is maybe more precise, then you get a smaller uncertainty, as in the case where you have only a very raw or a low resolution, then you get higher uncertainties. So these are the typical things we have to take into account. And also, if we are aware that we have different uncertainties, and for example, the standard measurement uncertainty here on the left side, let me just show, the standard uncertainty on this side is much larger than on the right side. And so also we have different risks to make a wrong decision. And I think you agree on the right side, where this probabilistic density curve is very small, then you have a low risk. You can be relatively sure that this indication really is shows that the instrument is conform. In this case here, where the probability density curve is much wider, where you have also some area outside here, the maximum permissible errors, then you, of course, you have a higher risk. So it really depends not only on your measurement standard, but also of the weighing instrument itself, the instrument itself under test, and also on the indication. So how to calculate measurement uncertainty? I guess everybody knows there is one basis, one very reliable basis, which is called the Guide to the Expression of Uncertainty in Measurement. It's called the GUM, the abbreviation, and as I already mentioned, you can download free of charge from the BIPM webpage or the OIM webpage, so both is feasible. So how to calculate measurement uncertainty? In the OIML guide G19, there's a chapter 8.2, which gives you some help. And finally, the guide specifies 5 steps to make it simple, let's say. But of course, one can also take directly the GUM, the principles, and you don't have to follow the guide G19. But I find it quite useful. And for this reason, I would like to describe a little bit what is written there. Sorry. So step 1. The first step is to describe the instrument under test with a whole measuring system. For example, we take such a balance, which you can find in a supermarket, just to weigh some fruits or some bananas or whatever, tomatoes. And what you do, you take a standard weight and you put it on the balance. And now you need to describe the number of tests you have to do. You also need to describe the uncertainty where you locate the standard weight, whether you put the weight really in the middle of the instrument. Let me just show you. Whether you really put it in the middle of the instrument, which means this position, or whether you put the weight somewhere at the edge on the balance, maybe at those positions here. All those things have an impact on the uncertainty. Also, you have maybe some uncertainty due to buoyancy effects. The buoyancy depends on the density of the surrounding air, depends on the temperature of the ambient temperature, and so on. And so you have to take all those quantities into consideration. And finally, also, you have to take the uncertainty of your standard weight itself. And as you know, we have this calibration hierarchy, or the hierarchy to the traceability to the SI units. And every single step of calibration, of course, results in some additional uncertainty. So that's fine. We can make a simple model. And for example, in our case, if we take such a balance, we can take, for example, the Euramet calibration guide number 18. It's also available free of charge from the Euramet webpage. And in the chapter 6.2, you can find some formula where the error of indication is described as the indicated value minus the weight or the mass of your standard weight. So that's a reference value of the mass here. So, and in the second step, now you need to describe the formula for the indicated value. And there are certain contributions to this indicated value. For example, the resolution can play a role. If you repeat the measurements, the repeatability can play a role. If you do some eccentric weighings, so that you put the weight on different positions on the weight instrument. So, and also the digital resolution of the instrument, and the same with a standard weight. It is, your standard weight has some nominal mass, but it also could have some additional uncertainty from the calibration, from the buoyancy. Maybe it shows some drift. Convection could play a role, which means that the air surrounding the weight also leads to some weighing effects. And in the seminar, I don't want to go into further details. If you are interested into such details, then please read this calibration guide number 18 or some other useful document. I think it's described in several documents, but it's just only by principle. You need to identify all the different kinds of tests which are necessary and which could have some contribution to the measurement uncertainty. If you have described all those contributions, then you have to calculate the associated measurement uncertainties. There's also some formula given here. Oops. And also, there's an equation for the variance, for the uncertainty of the indication, and there's a formula for the uncertainty of your reference weight. You have to do this, and finally, you have to calculate the sum of the variances. So the quadratic terms here, you have to add them, and then finally, really to come to the standard measurement uncertainty, you have to take the square root of this quadratic quantity, really to finally to get the standard measurement uncertainty of indication. And finally, step 5, you have to calculate an expanded measurement uncertainty of the error of indication, which means that you introduce such a so-called coverage factor of K, which is chosen in a way that the expanded uncertainty corresponds to a probability of 95.45%. And usually this factor is around 2, or in most cases it is 2, but not necessarily in all cases. But let's say it is 2, just to be simple in this seminar. So you have to, when I repeat it, you have to get the model equation for the indication for your reference weight, for your measurement standard. You have to calculate all the uncertainties, and finally you come up with a standard measurement uncertainty of this error of indication. That's fine. But what can we do with this result? How does it help us to go further and to calculate risks? So what we know is, we know the error of indication, the difference between 0 and between our reference and the indication. We also have the standard measurement uncertainty. That's also fine. And now we have the 2 parameters to describe this probability density function. As I mentioned, this curve corresponds to an exponential curve. And you can see here the formula of this exponential curve. And you can see here this curve has 2 parameters. It is mu, which corresponds to the error of indication. And there's a sigma also here. Where is it? There. There's a sigma, which corresponds to the standard measurement uncertainty. So after having performed the uncertainty calculation, so you have obtained both parameters to calculate this function. And that's great. Now you have really the essential tool to calculate also the risk. And I will show you how. So so we have all those two quantities which are introduced into this equation. The equation is described. We are happy, we are fine, and now we can go on and calculate risks. What is our task? We only need to calculate the areas under the curve inside the interval between the maximum permissible errors. So here in between this area, the inner area, and we have to calculate the outer area on the left side and also on the right side. So how to do this? Remember, we have the function itself. We have the parameters, we have the function. So that's a good starting point. And if we want to really to integrate this exponential function, then you get the so-called distribution function, which is the integral, as you can see here, of this exponential function. Unfortunately, maybe you know from math, from your studies at university, it is not so easy to calculate such or to do such an integration. In principle, if we look at the charts, it looks very easy because on one hand, you have this probability density function, and also the integrated curve, the distribution function, also looks relatively easy. But unfortunately, there is no analytical way really to integrate this function in a simple way. And for this reason, we need numerical integration. So that's just to keep it simple. We all have our computers, so it's not a big issue just to do the numerical integration and to calculate the areas. And you can see here on the right side, if you take this distribution function, the integrated curve, then at some point, where we have the maximum permissible error on the negative side, then we can read the area of the outer volume on the left side. The difference between this point and this point here, it means this is just the outer area plus the inner area, the outer area on the left side. So we need really this curve, we need to calculate this curve to get all those areas from this curve. So I think maybe you know from your studies how numerical integration works. That's very simple. In principle, it means we take, well, let me show you here. We take our exponential function. At certain points, we take the function value, we take the value of the function and multiply this function with a delta x to get some rectangle. You can see here many rectangles. And always it has some edge at the function. So you really only have to calculate the function, the value of your function at this point, multiply this by a little delta x, and then you get all those rectangles. And here in this chart, you see if we do this approach, then we do some little error. Sorry, on the left side here of the maximum, you can see that we always have the area of the rectangles is too small. We don't cover all the area under this curve. But on the right side of the maximum, we always count some area in addition, which is also not right. And you can see if we take the delta x and we do this and we make this delta x small enough, then the error we do is neglectable. So we can say we have only to calculate a sum of rectangles under this curve, and then we can calculate the whole area under this curve. Not so difficult. So I went to Excel just to show you how you also can do this very simply, in a simple manner. And first here at the top, here at the top, you can see I specified some numbers. I started with the mean value. 10 means the maximum, where the maximum located, where the the maximum of the indicated value is. So 10 means here just, so it's here, it's really the maximum of your curve. I specified the position of the maximum, the x value. In addition, I specified the sigma. Oh, where's my, there it is. Sigma, the standard measurement uncertainty, 0.1 in this case. I specified the maximum permissible errors, the interval from 9.7 to 10.2. And I also specified some little, some dt, some little delta, so which means the increment for this numerical integration. So I started with 9.5 because, as you can see, the value of the function of this exponential function is almost zero. It's sometimes 1.48 to the power of -5. And so I just went step by step. I put here many increments, and I always calculated the value of the function of this exponential function, the probability density function. And then I added another row, and I always multiplied this value of the function with the delta t, with a little interval, with an increment in x direction. And so this is the first rectangle, let's say. And then I calculated a second rectangle, and so on. I calculated all those little rectangles. And here in the fourth column, then finally I started with the first rectangle and added the second. So this number here is now the second. This is the sum of those two rectangles. And so I went on and every time I added another rectangle to get finally, this curve. So you can see also, if you follow the numbers here in the fourth column, you can see that it also rises up, and then finally it reaches almost 1. So you can read, for example, also at the maximum permissible error on the left side here at 9.7. What is the area? And this represents the outer area on the left side. So it is very easy just to use Excel to specify some quantities and to do this numerical integration with Excel, for example. And so that's really how I obtained all those curves. And just as an example, you can also get this Excel sheet from me. We will put it also together with a presentation on comet.net that you really can follow this example. There are some more examples. So it means we have to do this integration for 3 intervals. We have to calculate, we have to do the integration from -infinity to -MPE. In this case, it's 0.001972. That's the outer area on the left side. Then we have to calculate the area from -MPE to +MPE, which is the difference between those two numbers of this distribution function, which is this area. This is just the inner area. And again, from +MPE to +infinity. So on the right-hand side, 1 minus the value of the distribution function at the +MPE, and this is this area. So we have the outer areas, we have the inner areas, and inner area, and now we can calculate the risk. So we have this example. So the risk, you remember, hopefully, of an instrument considered to be conform, B non-conform, is the outer area together divided by the total area. And if we do this, so again, you can see here the integration. We just have to add this, we just have to add this number here and this number. This is the total outer area, and divide this by 1, by the total area. So this gives 1.85%. So the risk we have of our instrument, which we consider to be conform, that it is really non-conform, this risk is only 1.85%. And I think you would agree with me if I say, well, that's fine. There's a very small risk and we can be very sure, relatively sure, that our instrument is conform. So that's fine. That's what the example shows. So just to repeat, we only had to do the numerical integration to specify the area under the curve, to specify the area just up to the maximum permissible error, between the maximum permissible errors, and on the right side, outside the maximum permissible error. And this gives our risk. So that's fine. So in principle, congratulations to everybody of you. Now you are able to calculate risks in conformity assessment in legal metrology using measurement uncertainties in principle. So that's the most important thing behind this guide, that you are able to specify this probability density curve by some measurement uncertainty analysis, and that you finally do some little numerical integration, and then you can calculate the risk. So everybody can be happy. I hope you are happy. And now you can see the difference between the classical approach and this measurement uncertainty approach, this risk-based approach. Here in the classical approach, you only see the average value of the indication, the indicated value. And if it is within the maximum permissible errors, you say, oh, fine, instrument will pass. If you do this risk-based approach and you come up with some risk which you consider to be okay, or where you, for example, where you have also some negotiations with your client, with the manufacturer of a measuring instrument, and then you agree, okay, up to 5% or 10%, if we have such a risk, then it's fine, then it will pass. So you can see that there is really some different meaning behind, some different interpretation of the results. And that's what's really the interesting thing here. And now, coming back to our questions we had in some time ago, we already answered the third question. What is the risk for passing the test when it is non-conform? And what is the risk for failing the test when it is conform? So you are able to calculate both risks. You only need to calculate the areas under the curve, and then you are happy. But so far, we didn't answer the question, is a measuring instrument under test really conform? Can we consider this instrument to be conform? Or what is acceptable for us? Which risk can we accept? Which risk can we non-accept? So this question we didn't answer so far. And that's now why I want to go into some more detail with this question. And again, before we start with this next big chapter, I also propose to make a break. And I think it's just some minutes after the full hour. I think it fits perfect. And so I think my proposal is, are there any questions right now? Or then type them to the chat, and then we can answer. I will answer them when we start after 1 hour. So when we restart, when the next full hour will be. So is this okay for everybody, and especially for the organizers, for the CUMET Secretariat, and Yuri?
Питер, сейчас пока что вопросов записанных нет, но мы просили, что если кто хочет задать вопрос, это можно сделать устно. Поэтому, уважаемые коллеги, учитывая предложение Питера, пожалуйста, пишите свои вопросы в чат, в функцию вопросы и ответы, если мы увидим ваши вопросы, мы передадим их Питеру оперативно.
Я бы все-таки дополнил не просто в чат, в чате у нас технические вопросы, а именно
Вопросы-ответы. Да.
да, вопросы-ответы. Q&A, questions and answers. Пользуйтесь, это очень удобный инструмент, пожалуйста. И тогда ответы мы будем обсуждать на возможные вопросы, наверное, уже после обеда, поскольку сейчас у нас ничего нету. И обед у нас по плану до 2 часов по Москве, правильно? Мы уложимся, все зависит от Питера. Ну, насколько я понимаю, мы сейчас в графике, поэтому можем спокойно прерваться на обед и после обеда увидеть возможные вопросы и продолжить нашу работу. Я правильно понимаю, Надя?
Да, наверное, так и надо делать с учетом того, что предложил Питер, поэтому предлагается сделать перерыв на 55 минут.
Окей, дорогие коллеги,
I don't
друзья.
hear any English translation right now. So we guess we go for the break now, or yes?
Именно так до 2 часов.
Okay, fine.
Окей.
Коллеги, вы оставайтесь, пожалуйста, в
Then have a good
семинаре.
break.
Мы ничего не отключаем, поэтому после 2 часов, пожалуйста, возвращайтесь к нам снова.
Предлагаю продолжать.
Да, уже 14:00, поэтому, да, я предлагаю также продолжить.
Питер готов?
Okay, I think I can proceed. I just had a look to the chat, and there was one good remark, or respectively question. The question was why I have chosen the way to take the numerical integration instead of using some good statistical software package where I directly can have access to the distribution function and easily can get all those numbers. Well, that's true. So if you look at those figures here, of course, there are some statistical software packages like, for example, R, which is a, I think, well-known statistical software package. You can do that on one hand. I just wanted to show you really step by step how you can get those numbers if you don't have access to such software. So that's this was a, let's say, approach with some efforts. You can do it much simpler. That's true. So there's no question. So maybe to answer this remark. Are there more questions or remarks?
Да, Питер, есть еще два вопроса от участников семинара. Первый от Асылбека Жумагали. То есть с помощью оценки риска можно определить соответствие, но как изначально установить допускаемую неопределенность?
I don't hear any English translation right now. Yes. I don't know why.
Peter, I will demonstrate my screen and you will read the question.
Okay, fine. Fine. Okay, then I stop my presentation.
You can see my screen. Can you see my screen?
Yes, yes, I can see it. Okay, first question, that is by using risk assessment, we can determine compliance. Yes, I would say so. We can determine the risk, whether it's what is the risk of being non-compliance, for example. And the question, how to initially establish the permissible uncertainty. That's what I exactly want to cover in the coming 50 minutes, because this is a very, very interesting question. Second question, is there a generally accepted minimum number of observations in order to evaluate the probability of non-conformity risk with the specification, or should it be determined by the measurement calibration method? Also very good question. I think the minimum number of observations has a very high impact on the uncertainty. And maybe you know that if you do some calibrations, then you are always told to do at least 10, 15 observations that you get some sufficient low measurement uncertainty. However, in reality, sometimes, especially for verification, you don't take 15 measurements. You take some measurements, and then it really depends. Then you really have to calculate the measurement uncertainty with the number of observations you really do, and then you get the risk, and then you can decide on your own whether it's suitable or not, or whether you need more observations. Usually people are trying to simplify things and try to take only a few observations, but I'm also personally skeptic, because if you consider really the mathematics, the measurement uncertainty budget, the calculations, then the number of observations plays an important role. Also, I would not say there is a minimum number. you really have to calculate and to decide on your own. So what is really necessary in your special case? Are there more questions?
No other questions yet.
Okay, thank you. Okay, then I think I need to take over. And then okay. So now I want to proceed, and now there is some discussion about the risks, and also in combination with the so-called decision rules, because there are three fundamental types of risks what we can have. First is the risk of a false acceptance of a test. So we accept something which is not okay. Secondly, there is the risk of false rejection of a test result. So it seems the test result in principle is okay, but we reject it for some reason. And there's so-called shared risk, which tries to distribute the risk a little bit between the client or the manufacturer on one side and the test person or the test institution on the other side. And I will explain a little bit how this works. Okay, risk of false acceptance. So here you can see again the probability density function, and the mean value, the maximum, is within the interval of the maximum permissible errors. And so we would say, okay, the measuring instrument is considered to be conform. But there is some area outside, the blue area here, which also shows some probability that the instrument is not conform. And the risk is taken by the evaluator. So the evaluator has to say whether the instrument is okay or not. And it seems the instrument is okay, but there is some probability it is not. But the decision would be taken, it is accepted. For example, there could be a decision rule which says, okay, the test results are accepted if the risk is lower than 5%. This could be, for example, such a decision rule, and which you need to, to clarify with the customer. The second is the risk of false rejection. Again, we have an example where we would say, okay, the instrument is considered to be non-conform, but also there's some green area between the maximum permissible errors. Oh, yeah, here it is, the green area. And in this case, the risk in principle is taken by the manufacturer or seller of the instrument, because the evaluator says, well, the instrument is not conform, but there's still some chance that the instrument is conform. And so now the risk is by the manufacturer. What I have to mention is, and what's also clearly written in the OML guide, is there's no decision rule feasible for a given test that incorporates both risks of false acceptance and risk of false rejection at the same time. You have to decide, in principle, which risk you want to specify and where you want to have an agreement with the customer. And usually, as most instruments hopefully are conform, so most people agree on this decision rule, maybe acceptance if the risk is lower than 5%, something like this, or 10% or something like this. So that's usually the case. However, there's also some one approach which is called shared risk, which tries to have no advantage or disadvantage for the parties involved. And the precondition to decide on such a decision rule is that there is a sufficient small uncertainty of the error of indication. And I have this example here. Here in this example, you have two probability density curves. On one hand, there is this red curve, which I called or entitled the bad curve. And there's a very sharp green curve, which I called the good curve. In case the measurement uncertainty is very small, then you can decide very well whether the maximum is within the maximum permissible errors or not. And this is what I would call common practice. So people, all the testing labs or verification offices in the world, they try to have measurement standards, especially, which have a very small uncertainty compared with the maximum permissible errors, to be able to decide easily whether the instrument is conform or not conform. And so this would mean that you really have to take a standard, a measurement standard, which is really good and which has this very small measurement uncertainty. And this is also important for the chapter 6 in the OML guide, because the chapter 6 deals with conformity testing or conformity assessment decisions that do not explicitly incorporate measurement uncertainty. And it's written measurements outside a lab. So there is in principle no need to calculate the measurement uncertainty for every measurement if there is always an underlying understanding that the level of uncertainty in the measurement results has been assured and the method of the assurance is well documented. In other words, if there's a good understanding of all the relations between the measurement standard, the measurement, the testing procedure, and the corresponding risks, the corresponding measurement uncertainties, and if it is small enough, then you don't need to calculate the measurement uncertainty for every measurement. But in principle, this is a simple approach. And for this reason, I would like to proceed now with some examples, really, which show the influences on the risk and what you have to do to come to good results. So that's what my intention now, and to fill this guide a little bit with life, because what I described so far, these are the contents of the guide, but the question is really how to deal with that, how to play with the numbers, let's say. And that's what I want to describe now. So I already showed you these Excel sheets, how I calculated the area under the curve and so on. And as we need some underlying understanding, now I would like to have a closer look to all those parameters. And one essential parameter is the standard uncertainty of the measurement. So you can see here on the right-hand side, the probability density function, you can see sigma, the standard deviation, which is really an essential parameter. If it is small, then the whole curve is getting sharper and sharper. But if it increases, then the whole curve widens up. And that's bad for our application in conformity assessment. So I started this example with a standard deviation of 0.1 in this example. And the question is now, what happens if we increase this standard measurement uncertainty? Just if we have some idea that maybe uncertainty is bigger. And I made this little table for this example. We have this balance, we have this standard weight. And for example, if I take some standard weight or some procedure which shows a higher standard uncertainty, then you can see how the risk increases. Where is my cursor? There it is. So we started with this example with a standard uncertainty of 0.1 kg, and we already had obtained this risk of 1.85%. If I increase this standard deviation by only 50%, so let's say 1.05, immediately the risk rises up to 10.5%. And if I increase the standard deviation even further, then you can see how the risk increases. So it means a small increase of the sigma of the standard deviation leads already to a big change of the risk. And that's a reason why also the measurement uncertainty of the standard should be very small or relatively small, that you are able to judge the conformity of the product and to have some really small, low risk. And here you can see the corresponding probability density function for those examples. So I started with sigma equal to 0.1 kg, and you can see the risk 1.85%. If I increase the standard deviation, then the maximum moves down, the whole curve gets wider, and the risk increases to more than 10%. And so on for higher standard deviations, there is the risk here of more than 20% or even more than 45% if this probability function really gets so low. So it means the uncertainty of your standard and also the standard of your the uncertainty of your test procedure should be relatively small, that you are able to have some low risks. So our conformity assessment procedure should result in a narrow probability density function. That should be our intention. So, as I already mentioned, part of the overall uncertainty of our measurement uncertainty is also the contribution of the measurement standard. There's always some part of it. And people say, well, this uncertainty should be small enough that it has only a little impact on the uncertainty of the standard measurement uncertainty. But what does it mean, small enough? How small should the contribution of the measurement standard be in terms of uncertainty? And this exactly leads us back to this practical question: should it be 1/3 or 1/4 or 1/5 or whatever? So what fraction should this measurement uncertainty of the measurement standard be compared with the maximum permissible error? And to follow this question, I had a closer look to the uncertainty of the measurement standard. And now I will discuss the question, what should the ratio be between sigma, the standard deviation of the uncertainty of the measurement standard, compared with the maximum permissible error for the instrument under test? So this is the question. And now we take an example. Back, we have this balance, and we just think of a simple commercial balance, which you can find in many supermarkets. Maximum load 15 kilogram, and the so-called verification value, which is also at the same time the maximum permissible error, is 5 grams. And as a standard, we take, as a standard weight, we take a 10 kilogram weight, and we just say, well, we take a weight according to the OIML R111, and the only question is, what class should we take? What class of precision should we take that we can get finally good conformity assessment, good decision? So if we have a look to the OIML R111, maybe most of you know this table, which is, it's a long table. I just took only a little part of it. Here you can see the nominal value, and I took only this row here, or this part with the 10 kilogram. And here you can see all those OML classes from E1 finally to M3. And here in this table, it is written how many milligrams, or what is the tolerance for this weight. What is the maximum permissible error for this weight, for the 10 kilogram weight? For example, for the E1 class, it means that it should be within 10 kilogram plus 5 milligram and 10 kilogram minus 5 milligram. So this is just the range which is allowed for the weight for such a high quality weight. If we go down to class M3, on the other hand, then you can see here there's the maximum permissible error is 5,000 milligram, which means 5 gram. And so it means 10 kg plus 5 gram and 10 kg minus 5 gram. So, but from those numbers, and especially from this information, the maximum permissible error, there's a discrepancy. Here in this table, maximum permissible errors are given for the weights, but what we need to think of risks is a standard measurement uncertainty. And unfortunately, this is, on one hand, the OML R111 is simple, it's practical, but for our purpose, it's not the right information. So the question is how to calculate the standard measurement uncertainty, the sigma, from those numbers, from the maximum permissible error for the weight. And that's relatively easy. And so fortunately, there are guides, there are documents how to do this. And I just took an example which is very familiar to me. This is from the PTB, the German Metrology Institute, from its DKD, which is a part of PTB. The DKD is a so-called German calibration service, and they issue very good guides. And one, this number 7.2, deals with a calibration of non-automatic weighing instruments. And in this guide, there's a chapter which exactly describes how to calculate the standard measurement uncertainty of a reference weight. And again, we have the nominal value of this weight. Here it is, MN. Then there is maybe a correction compared with the conventional weighing value. We have maybe a contribution from buoyancy. We have maybe drift. We have maybe, again, convection effects if the temperature of the weight and the balance are totally different or different. And you can also calculate the corresponding uncertainties for that. So that's the guideline for the calibration of non-automatic weighing instruments. And in this example, there's some information given what really to do. So, for example, in our example, there's the nominal value in this is 10 kg of our weight. The second term, in case of R111, you can describe the uncertainty by this tolerance. For example, 500 milligram for M1 weight, which means the maximum permissible error from the table. Then the third term, the buoyancy, there is a formula where you can also have or need to take the densities of the weight and also of the surrounding ambient air, and also the maximum permissible error. Then you have the drift, and there's written if there is no information about the drift of this weighing of the standard weight, then drift should be taken the maximum permissible error. And finally, There's also some description for the uncertainty for the convection, for convective effects. There it is written, it is some number divided by the square root of 3, but it's only relevant for class F2 or higher. But in any case, also there's a table given where you can get this number. And I will show you in a second. So here you can see this table to take care on convection effects. So again, you can see for 10 kilogram for weight, you can see in terms of the difference in temperature between the weight and the balance. So what correction you should apply or how you can calculate the uncertainty from that. So that's relatively easy. We have everything what we need. And then I did some little Excel sheet calculations. I calculated the corresponding uncertainties. So for the conventional value for the buoyancy, I took some formula with the numbers for drift and also for the convection terms. So I did some estimates, for example, for the convection. I thought of a temperature difference of 5 Kelvin between the weight and the balance. Usually it should be less, I guess, but just to have some guess, I took this number. And what is also important, the buoyancy term, the uncertainty for the buoyancy, this is a relative measure. It's not an absolute measure. And for example, the result, the number was 8.08 times -5. And this number has no unit. And so it has to be multiplied with 10 kg with a nominal weight, really to get the contribution in our case. So that's a little thing you have to take care of. So now you can see the equation for the uncertainty with the 4 contributions. And here in this little Excel sheet, I calculated the uncertainties in milligram, kilogram, milligram, milligram. And so just to compare it, I transformed everything to gram, just to be able to compare it. And you can see really that the biggest term is the drift, because we took some very simple approach to describe the drift. And for example, convection, as it was mentioned in this guideline, is extremely low, and in principle compared with the other parts, it's neglectable. So that's almost nothing. Finally, there is an uncertainty of 3.01 gram. And what is remarkable is that this means it is 60% of the MPE. The MPE is 5 gram. So if we have such an uncertainty only coming from our reference weight, from our measurement standard, this is quite a lot. This is really very much. And as I mentioned here, the reason for this high number is because we have this very high contribution of the drift. And it makes sense in such a case really to get numbers for the drift of the weight, of the standard weight. And usually you have a weight which is characterized already several times, which you know very well. So this is in principle non-common, I would say. But anyhow, it helps us just to explain some effects in terms of risk. And that's the only thing which is relevant for us. And for this reason, I took an assumption. For a moment, we neglect all the uncertainties from the indication from our measurement procedure. We just say, well, the standard measurement uncertainty is dominated only by the measurement uncertainty of the measurement standard. So in terms of the equations, we know the uncertainty should be calculated this way in principle. But for a moment, we simplify everything. We say, well, that's almost, or that's zero. So we have to neglect this equation here. We only take the uncertainties of the measurement standard to keep it simple. So if we do this and take exactly this example, then we get a risk of almost 10 to 11% only from the reference weight, from the measurement standard, with the assumption which we have taken, so no uncertainty contribution from the indication. So it means we have a small uncertainty, or no, we don't have a small uncertainty. We have a risk coming only from the reference weight of 10%. And then I did some calculations. I took this as a starting point. This is a M1 class weight with 500 milligram as a maximum permissible error here. So you just saw the uncertainty of 3.01 grams, leading to a risk of 10.64%. Now I calculated the uncertainty for better weights using exactly the same approach. And there is some slightly smaller number, but you can see it's almost the same. Because in all those calculations, I took the same contribution of the drift in this uncertainty calculation, which is maybe also not reasonable, but I just took it. And you can see if you have such high impacts on the uncertainty on a standard weight or standard measurement standard, then you can't get down with it. So you maybe you take a higher quality weight, but you can calculate the same risk as long as you don't change your uncertainty budget calculation. On the other hand, if you take some weight which has a lower quality, higher uncertainties, then you can see that the risk increases, for example, here to 12% or 24%, and that's really what we can expect. But this gives us only some idea that we really have to be, not just to take a very good standard, which is maybe much too good for our application. We have to balance somehow the uncertainty budget calculation, the quality of the standard, and then also the risk. So this was not so successful. We have to improve our uncertainty budget calculation. And now I did also some simple assumptions that also better standards also will finally have a smaller uncertainty, what we can expect. So standard measurement uncertainty of the indication, this part, I assumed that it equal to the uncertainty of the standard weight. Just to be very simple, just to say 50% uncertainty comes from the indication, from the measurement procedure, 50% from the measurement standard. In reality, it might be different. It is just only an assumption just to get some idea what happens with those numbers. So, and in addition, I said, well, the buoyancy effects also should be more investigated, should be taken better into account in our uncertainty budget. And just to be very simple, I just assumed the better the standard, also the lower the buoyancy contribution. And I just said, well, okay, I decrease it by 10% with every better class, for example, starting with M1. So that's what usually would a lab would do. The better the quality of the standards, the more efforts are taken for those contributions. It's the same for the drift. Also, I took this simple assumption should be the same magnitude as the buoyancy. So also better standards have smaller buoyancy uncertainties. So if you go this way, which is far more realistic, then again, we have the starting point of our M1 weight, But now you can see if you have better standards, better reference weights, then those uncertainties go down. That's what you also expect from a calibration certificate for such standards. The error of indication I kept always the same as here for the M1 weight. And then finally, if you take those both contributions, the uncertainty for the reference weight and also the uncertainty for the indication for the testing procedure, and calculate the variances and so on, then you get finally those uncertainties for the error of indication. And that's now quite interesting. Here you have a combined uncertainty of 3.18 grams, leading to a risk of 12.6%. And if you take a class which is better, then also the uncertainty gets better, but only a little, because the error of indication is always very high. It's much higher than the uncertainty coming from the reference weight. And again, or if you go to the right, if we take some weight which is shows a lower quality, then you can see also how the uncertainty increases and also the risk increases. And if you compare this with the uncertainty with of the reference weight with a maximum permissible error, which is 5 grams in any case, then, sorry, I need to go here. So if you compare or build the ratio between the uncertainty of the standard weight and the MPE, then finally you can see here really the percentage. So this would mean in the green line, the F2 weight, this weight, the uncertainty would have about 20% of the maximum permissible error and would lead to a risk of 12% in total. So if you take a better standard, for example, the E1 weight, what nobody would do, then of course you could reduce this percentage to, where is it, 13.8%, but it doesn't help you very much if the testing procedure has such a high impact on the overall uncertainty that you still have this relatively high risk. And the same here on the other side, the risk rises up to 60 or 80% if you take really some weight, some standard weight, which is not suitable for this application. And from that, you can see very well that you have to take a class or a weight, a standard weight, where the uncertainty is small enough that you get some reasonable risk. But if you take some better weight, usually it doesn't help you because the uncertainty of the whole procedure is such high that you don't need a better standard. So in other words, the choice of the right standard for each conformity assessment task is really essential. And for this reason, if you think of these 1/3, 1/4, 1/5, and so on, here you can see, for example, in this case, 1/5 would be a good solution, would be concerning the risk and the result. I think this would be quite reasonable to take such a F2 weight for such purpose. So, okay, but this is just only a part of the truth. Even if we take such an F2 weight and we get this probability density function, which you can see here on the left with a risk of 12.6%, if you have some indication during the testing process that the indicated value moves to the maximum permissible error, of course, then your risk increases. So even if you take a good reference weight and you apply it then for a testing procedure, then of course you could have also risks of 50% or even more, or also less, depending what results you really obtain, how really the instrument under test behaves. So we should not forget about that. So the 12.6% are really the lowest risk what you can obtain for a certain standard weight and a corresponding balance and a corresponding testing procedure. This is this example. And for this reason, you should try maybe to reduce the uncertainty of the testing procedure, that you get much sharper probability density function, that you can have smaller risk and can get better decisions. Okay, now I would like to conclude all this, what I showed you today. So the conclusion number one is, if we compare the classical approach and the risk-based approach, in both cases, we have to determine or have to measure the error of indication, which means the difference between the indicated value, which is 682 in this case, and the 650 kilograms, for example, from the reference weight. That's starting point. In any case, we have to do this. Conclusion number two, the error of indication should be within the interval between minus MPE and plus MPE in both cases to decide that the measuring instrument is conform. It's also no surprise for you, I guess. So in both cases, you would say, if you have such results, okay, it's fine, the instrument is conform. No surprise. Conclusion number three, when we really consider the risk-based approach, then we have to calculate the standard uncertainty of the error of indication, which means really, where is it here? So in this case, the standard uncertainty, which shows you how sharp or how wide this probability density function is. So in any case, as soon as you want to have some idea about risks, you need to calculate this standard deviation, standard uncertainty. Conclusion number four, by applying integration in respect also to the MPEs, we can calculate the area under the probability density function to determine the areas inside and outside the MPEs, and then we can calculate the risk. So it's also no big issue. And conclusion number five, there is some kind of numerical integration necessary. You can take this approach. You can take also some statistics software package like R, and then you easily can get all those numbers, and then you can calculate the risk. No difficult thing. And conclusion number six, there is a risk of a conform instrument being non-conform. As I've shown you, you have to consider the areas or the values of the distribution function. So that's your chance to get numbers for the risk. And also there's a risk of an instrument which is considered to be non-conform, being conform. And you can also calculate those areas, and then you can find out what is the risk for that. So I hope I have explained sufficiently that in the case of the risk-based approach, you need to balance the different aspects. You need to balance the uncertainty of the measurement standard compared with the uncertainty of the indication, so let's say the testing procedure, and also the given MPEs. And as it is also written in the guide number 19, so usually a typical uncertainty or typical ratio of this is 1/5, which means that the uncertainty, the standard uncertainty of the measurement standard, should be 20% of the given MPEs. So that's a good guess, but of course, according to the guide, to the principles, you are able to calculate it on your own if you take everything, all the uncertainties into account. So, final conclusion. What does the OML guide G19 tells you? You can do conformity assessment, let's say testing, inspection, verification, whatever. And if you follow those principles, you can calculate the risks. But in any case, whatever we do, if we take the risk-based approach, we have to believe somehow. We can't never be 100% sure there is a risk, and a risk means you can be wrong. There's no 100% right decision. But I think we can live with that. If the risk is, let's say, 5% or 10% or something like this, and then it's fine. There's no problem with that. Okay. So that's for a moment. Yeah. Are there questions or remarks to that?
Да, Питер, я бы хотел сказать, что у нас есть две поднятые руки, во-первых. Это по порядке поступления, если я не ошибаюсь, руку поднимал Харри Штольц.
I don't hear the English translation, I'm sorry. I don't know whether I have the wrong...
Юрий, наверное, потому что у тебя не включен канал перевода.
Я на русском канале.
Странно.
Я перепроверился. Я, если это удобно, могу Питеру и на английском задать вопрос принципиально.
Ну, давай, наверное, так. Я не знаю, почему не слышно.
Peter, I have to say in English, and we now can see at least 3 hands, raised hands. First from Harry Stolz, the second from Mazar Gurbano, and I see also the raised hand from Nadia Efremova. Надя, я думаю, что мы должны для того, чтобы вопросы прозвучали, перевести соответственных участников в возможность их выступить, так как мы и обещали. Я правильно понимаю?
Да, сейчас сделаем. Азербайджанский институт метрологии переведен в члены группы и может выступить. Коллеги, включите, пожалуйста, микрофон и видео, если вы считаете нужным.
Коллеги, мы хотели бы вас видеть.
Sorry, it was a mistake by me. I didn't have any question.
Окей. Окей.
Коллеги из Азербайджана, пожалуйста, включите микрофон, и вы можете тогда задать свой вопрос.
К сожалению, мы не видим и не слышим коллег. Коллеги? Ну, давайте тогда попробуем дать слово Надежде Ефремовой.
Ну, тоже как-то странно, что-то у нас проблемы с подключением участников, которые хотят задать вопрос, хотя Гарри смог прокомментировать. Ну, возможно, коллеги, тогда есть предложение, может быть, тогда напишите ваши вопросы в чат.
Я хотел это предложить.
Вопросы и ответы.
Да, в раздел «Вопросы и ответы», пожалуйста, напишите, чтобы вопросы не остались неотвеченными. Нам бы этого не хотелось. Я надеюсь, коллеги услышали, и мы получим в чате, ну, соответственно, в разделе «Вопросы и ответы» соответствующие обращения. Сейчас у нас по плану кофе-брейк. Мы можем прерваться до 3 часов.
То есть встречаемся через 10 минут.
Совершенно верно. Питер, нету возражений?
So we have the break until the full hour, right?
Yeah.
Okay.
Да, именно. Коллеги, встречаемся ровно в 3.
Надя, добрый день. Ты хочешь все-таки задать вопрос? Не понимаю. Я написала ему об этом в чате. Хорошо, хорошо.
Peter, can you make sure that you've chosen the English channel?
I don't have access to this option anymore. I don't know why. I just was looking, usually it's on the bottom to the right, but now the Zoom software shows me some different options here. I don't have the chance to switch to English or Russian or whatever. I don't know why.
Может, тогда нужно ему переподключиться в вебинар?
Maybe you should rejoin.
I will try.
Надя, какие-то технические вопросы возникли, я так понимаю?
У Питера пропала функция перевода, как мы поняли, поэтому какие-то проблемы с переводом.
Ох.
И он говорит, что у него нету этой кнопки управляющей, поэтому, возможно, сейчас попробует переключиться.
Ну, когда мы переключали канал, она на какое-то время, я имею в виду для переводчика.
I can't find this option anymore. I have a different view here on Zoom. I don't know why. I have no chance to choose the language. Maybe Euro, if there are any questions, could you please translate for me?
Это не поэтому.
Did I hear anything?
Давайте мы не будем переподключаться. Если нужно будет, будем переводить. В прямом канале, Надь.
Да, давайте так, потому что сложно прокомментировать. Мы не знаем, какие у Питера, из-за чего сложности, поэтому нужно подстраиваться под ситуацию.
Peter, do you hear me?
Yes, I hear you.
Okay, let's do that way. We have only the 1 hour.
Yes.
To the end of webinar. Let's do not change the connection and change the links and so on.
Yeah.
I will try to translate if it would be the possible for the next questions and so on.
Now the sound is off.
Okay. Do you hear me?
Yes, now I hear you again.
Okay.
Да.
I will try to translate in the direct channel without the translation, okay?
No, sorry, again you're off. I don't know why.
Только вопросы, Юрий. Основной перевод идет через Дениса и Константина.
Do you hear me? Я сейчас в отключенном канале. То есть без перевода. Я просто без перевода. Пробую подключиться на английский. Peter, do you hear me? Peter? No.
I don't hear anything right now.
Юрий,
Я слышу, я сейчас на русском канале, я слышу, я пробовал переключиться.
No, I can hear you, Yuri.
Do you hear me now?
Yes, I hear you now, yes.
Юрий, давай
Yeah.
тогда так и попробуем, потому что сложно
Yes.
сказать, почему у Питера пропала управляющая функция перевода. Мы не сможем сейчас разобраться и просто будем терять время.
Да, чудеса зума. Тогда я буду общаться, если это будет касаться вопросов, я
Да.
буду общаться на канале с выключенным переводом.
Да.
Окей, а сейчас я переключусь все равно на русский канал для того, чтобы была возможность слышать перевод.
Да, все верно.
Окей. Peter,
Yes.
I will translate the possible questions on direct channel without the translation.
Okay.
Not the lost the time. We have not a lot
Okay.
of time.
Yeah.
Okay.
Mhm.
Юрий Владимирович, есть два вопроса от представителей Белгима. Один я перевел и могу точно так же показать на экране. Второй, вот он только что поступил, я еще не успел. Поэтому...
Peter, we have two questions from Belgium.
Yes.
The first one, Igor had translated and can show on the screen. If you stop the share your screen, you will see that. Okay.
Yeah, I can read it. Well, the question is based on the presented slides and formulas. The distribution function is assumed to be normal, Gaussian type. This is an a priori estimate of the distribution function. How can we trust this statement based on the number of measurements announced? Is the distribution type checked and by what criteria? Yeah, good question. So, of course, I showed you the let's say the simplest case with a Gaussian distribution. As long as you don't have any other information that your observations belong to another distribution, so long you can take the Gaussian distribution, because this is what say in the technical field, I think the most of the measurement systems behave according to the Gaussian distribution. But of course, if you have some, how to say, some information that this in your special case, this is not the case, then of course you should also deal with the corresponding distribution function you have. I think the part of the question is that you should have a sufficient number of measurements finally that you also can trust that you have a Gaussian function. And as I mentioned before, you have to have, according to the general principles, at least 10 to 15 measurements. This would mean 10 to 15 observations to really to be on the safe side. Let's say that you have some Gaussian distribution and that you can also have a good estimate of the uncertainty. However, in reality, if measurements cost money, then people try to reduce the number of measurements, and then you have to calculate what happens, because the measurement uncertainties will increase and the risk increases, of course, because if you take only a few measurements, I don't have the final answer to this. In principle, if you take less measurements than, let's say, 10, 15, if you take, for example, 5 or something like this, then of course you have a high risk, and then you have to decide on your own what to do. How do you deal with this risk? And that's what I can say to this topic. I don't have a good answer to this. It really depends. That's why people usually should do such risk assessments or such risk calculations, that you really have an idea how large the risk is, what you are doing there. Okay.
Peter, we have a second question.
Yes.
Igor didn't have enough time to translate it and to show to you on the screen, but I try to translate online. It's concerning of the document. I believe it's ILAC G8, if you know what I mean.
Yes, I think so.
It's and that document present the method with the name of method of assurance band, or kind of special area to be sure that we have no additional risk, if you know what I mean.
Yeah, some band of confidence or something, some area of confidence, I think.
Yeah, this method, it's a quote. This method consists that we have a shift of MPE for the quantity in accordance to the combined uncertainty. That approach can afford us to not to concern the risks or false acceptance of the measurement instruments during the calibration, and simplify the procedure of the calibration. In practical, the objective of this shift of this method, it's a so-called traditional approach. What do you think about it?
Sorry, the sound was gone again. I'm sorry.
It means the question
I
is.
can't hear you now.
No? It's a magic. It's a kind of black magic. Do you hear me?
Now I hear you, but you are frequently interrupted. I don't know why.
I have no idea. Now?
Now I just hear you, yeah.
It's so-called traditional approach. To not calculate the risks. No?
Sorry, your sound is gone.
Okay, let's do translate and share the screen. Igor, sorry. Let's go further, and after that we discuss it at the end of this hour. Okay.
Yeah, then I proceed. I guess it's maybe better.
Something wrong with the Zoom, I believe.
Yeah. Anyhow, I think it's then I will proceed. Okay. So the last topic I wanted to cover is the software. And as we discussed already, to calculate the measurement uncertainties, that's a very important thing. And usually you can do this, for example, with Excel or similar programs where you have some spreadsheets and where you can also easily calculate uncertainties. However, there's specialized software available which also guides you through the process, that you really specify your variables and your uncertainties, and that it automatically calculates the uncertainty budgets. Before I go into detail, maybe one disclaimer. So I have no contract with any of the manufacturers of the products which will be introduced. I have no advantage. I didn't get any of the commercial software free of charge or any gifts or whatsoever. All the information is just my personal independent opinion, nothing else. So I'm totally free. There are two very interesting articles from the internet where people already did some comparison on uncertainty analysis tools. There's this interesting article from 2004, which is still up to date, to my opinion, and which covers many different software packages, which is quite interesting. And I will also put a copy of this article to the comet.net together with this presentation. And there's another article also from 2005, also I would say more or less up to date, which also compared software packages for uncertainty measurement calculations according to the GAM. So that's quite helpful. And so I will also cover most of those software packages which are still available also nowadays. And what is also very interesting, there's one very nice internet page where a nice guy compared also 8 free uncertainty calculator software packages, and which can be downloaded. And I will give you now an overview over all those commercial software packages and the corresponding freeware packages. And there might be even more software packages. I guess I don't cover everything, but maybe I cover all those uncertain software packages which you can find more or less easily. So I'd like to start with the commercial software. There is a software called At Risk from the USA. There's also the web page where you can find information. There's a software called Crystal Ball from Oracle, or let's say from a staff member from Oracle who published this software under Oracle. Then there is GAM-SIM from the German company Quodata. And there are 4 more commercial software packages. There's a GAM Workbench also from a German company called Metrodata. QMSys from the company QMSys, GAM Standard. It's from Bulgaria. Then there is Uncertainty Sidekick Pro, also from the US, and software which is called Uncertainty Toolbox, also from the US. So, and I will guide you now through all those software packages. I will start with At Risk. According to the information on the web page, I also put the costs here, the prices to the presentation, that you can get some idea, that you have some idea about the costs. At Risk is a software which it's an add-on to Microsoft Excel, and it lets you do Monte Carlo simulations, which is quite good, which is a very good approach to calculate measurement uncertainties. However, this software is not specialized for measurement uncertainties. You can calculate, or you can take Monte Carlo simulations also from many other applications. So it's not a specialized software. Here you have some screenshot that you can see that's also, it is able to calculate some distribution functions, which is most probably not bad. However, it's for beginners, I think it's hard to understand. And for all of those who are not familiar with Monte Carlo simulations, I just want to say a few words what is meant by this. So I guess you know Monte Carlo, this little state at the southern part or coast of France, which is an independent state, a very small state, and they are famous for all their gambling casinos. And that's what you can see here on the left, that you really throw some cubes. And when you throw such cubes, in principle, the numbers are equally distributed. You can have the same probability to get a 1 or a 2 or a 6 or whatever. You can apply this as a software to find solutions for complex problems. Here's just a very simple problem, which just means how to calculate the area, which is this quarter circle here, which is indicated or highlighted in yellow, and how you get the area of this quarter circle. You just do you do, for example, 1,000 or 100,000 simulations, which means that you throw the coins, the cubes, and it means so you just by chance you take the numbers and you take one number for the x coordinate and one for the y coordinate. How is it here? So you always have a pair of numbers, and if you count all those events which are inside this yellow part and compare this with a whole quadratic area, with the whole rectangle, then you can get the number of points inside as a ratio to the number of all points. Then you can get the yellow area just by counting all those events. So this is just to get an idea how this works. And if you think of probability distribution functions of measurement uncertainty, then let's assume that you have a simple system, a simple quantity which is dependent of two influence quantities, x1 and x2. And both x1 and x2 have their own probability density functions corresponding to their measurement uncertainty. And now what happens, you do a simulation, or you do, again, thousands or 100,000 of simulations, and every time you choose a number of this probability density functions. And I tried here to show you this red lines. For example, one simulation would mean this information for x1 and x2. And then you do the transformation, you do the calculation of the measurement uncertainty for the final quantity, and then you get the corresponding uncertainty and the corresponding probability density function for the quantity you really want you described in advance. So this is just how Monte Carlo simulations work, also to estimate some measurement uncertainties, also of complex problems. So, and this is also true for this software, which is called Crystal Ball from Oracle. This gives you the chance also to calculate probability density functions from Monte Carlo simulations. It's also not specialized for measurement uncertainties. Costs around $1,000. And if you really are highly interested in Monte Carlo simulations, I think then it's a good choice. Then you really should do this. But it's not for beginners, not just to start some, let's say, easy calculations or for measurement uncertainties. So the next is GAMSIM. This is from the German company. This is, here you can see also on the screen an example. This software also uses the Monte Carlo method for the evaluation of measurement uncertainty. It's really easy to use. It's a good interface. You are guided through the process. First, you specify your quantity, how it depends on all the other input quantities, and then you are forced to enter all the data of the observations or the corresponding uncertainties. And then it takes only a short time to calculate the results. And this is also a software which is suitable for beginners, which is very nice. And there's a free trial version available that you can try out in advance before you buy anything. The price, 840 euros, also not cheap, but I think that's, if you are a beginner, if you want to have some nice software, I think then it's also a good chance here to take this software. You can try it out. Next one, so it's also how it works. You have to, first you have to start with a model. For example, here is this AX. This is some current, I guess, how it depends of some on some resistors and so on. And then you can type in, here it is written, the type A data or your observations. If you have taken several observations, you can, if you have some correlation between the quantities, and then you can have also a summary report about your uncertainties. That's quite good. That's really easy. And then here's an example of a result. That's a uncertainty budget, the report, that you really have a good overview also about the uncertainty contributions here, the sensitivity of each parameter. So that's quite nice. And there's also a YouTube video which explains the software a little bit. You can find also the link there. And then you can have some kind of demonstration how you can work with this system. That's quite nice. Sorry. So next is a GAM workbench, which is more or less similar. It doesn't, or it uses also Monte Carlo simulation, but also, let's say, it can also build partial derivatives numerically. And you start with a model equation. You type in your system, then automatically it generates items for each quantity that you are able to type in some description, to type in your observations and such things. It's quite nice. There's also a YouTube video available which demonstrates the software. For example, here there's one quantity which has got a type B uncertainty. Then you can also choose what kind of distribution function, the value, the expanded measurement uncertainty, and so on. You can also import from Excel. If you have many observations, for example, then it's very easy to import the data. And you get a very nice overview, a very nice report. I worked with the software for many years at PTB. It's not cheap, but it's a very nice software. And I can recommend it also for beginners. I think that's very easy to use. That's really, you are guided through the process. That's really good. The prices are relatively high. It depends whether you want to have some single user software license or whether you want to have some network licenses. So it really depends what you want to have. What is important, it's available in English, French, Spanish, and German. I think, unfortunately, not in Russian. I'm sorry. But I think it is quite a good software. Then there is this QMSys. This software is available at different levels. The most expensive is called the GAM Enterprise. And with this software, you can use Monte Carlo simulation as well as also the so-called uncertainty propagation by linear models, which means the calculation of partial derivatives by numerical estimates. Then you have the GAM professional version, which offers a little bit less, where the results are validated with using the Monte Carlo method. And there's a GAM standard method, which is the simplest version, which also allows the common procedure and no Monte Carlo simulation. And there's an educational version available with limited functionality, but it can be freely used. You can try it. You can also get some idea whether it fits to your workflow, whether you can deal with the software. And you can see here the prices also depending on the number of licenses. It depends very much. I was a little bit irritated because here it is written GAM calculator. I think it means GAM standard because this is let's say lowest price. But I think one could give it a try. I think it's a good software. You can see here also how it looks like. Again, it's the same. You start with a model equation. What is very nice, you can type in with the most basic equation, you can start. And if there is one quantity which also depends on many other variables, then you can also type in all those other equations. You can have many equations. You can describe complex systems, and it's very nice. You can get some good overview over all the uncertainties here. You are guided through the process. Also for beginners, I think it's very nice. It's maybe one of the cheapest softwares on the market if you start with a standard version. But I think that's quite nice. Also, what is possible to import data from the MS Excel. So that's also quite nice. And here you can see also how it looks like the budget report. Sorry, I need to go back. So that's one budget. That's a report you get finally that you can also document your results. That's quite nice. Then there is Uncertainty Sidekick Pro, which in the simplest version is also relatively cheap, $295 for a single user software license for one PC, but there are also other licenses available. This is a software which also guides you through the process, and you can see here on the left, there are some rectangles with 1, 2, 3, 4, 5. And also you can start typing in the model function, and then you have to type in the data and so, and the system also assures that you don't forget anything, that you type in everything what is necessary. And it also gives you a nice report. Import from Excel is also possible. And there's also, you can also type in different equations if you have complex systems. That's really, really nice. And that's, for example, the report you get finally. It's more or less always the same. You get, for every quantity, you get the standard uncertainty, you get degrees of freedom, also sometimes to which percentage it contributes to the overall uncertainty. That's quite good. Then there is the uncertainty toolbox. This is just taken from the web page. And this is not just really a software, it's an add-in for Microsoft Excel, for all those people who enjoy to work with Excel. I think could be a good choice. For me personally, I would like to have really a software. The prices are also relatively high, even if it's only in quotation marks an Excel add-in. And it also gives you some framework. You get some Excel sheet, which is also with different colors, where you can type in your function, your model function, where you can type in the data, and sometimes then some windows pop up, and then you can just type in the formula or the data. So it's also not bad, I guess. Here, for example, you can type in all the measurements, the observations. That's not bad. So in principle, it really depends on your personal choice, and I think I recommend that you try out in advance before you buy, for example, anything. Then there are fortunately, some freeware software packages available. I will introduce the Gumtree calculator. That's a software from the Measurement Standards Laboratory of New Zealand. And fortunately, they just put it on their webpage, or on a webpage that you can download it for free. Then there are demo versions for the already introduced QMSys GUM standard software. Also GAM workbench. Also, there's a demo version available free of charge where you already can do something. Then we have the new kit, Measurement Uncertainty Kit. That's from a Finnish institution, environmental agency from Finland. It's also interesting. And then there's the so-called NIST uncertainty machine from our colleagues from the NIST in the US. There's also nice software, Hewlett-Packard, uncertainty calculator, Uncal 3.2, by a guy called Chris Grachanen from Agilent. There's Uncertainty Sidekick. This is a free version of the Sidekick Pro. It's a commercial software. And there's from our colleagues from NPL, the NPL Measurement Uncertainty Software. And I will just go into detail a little bit. So the Gumtree calculator is a little bit special, I would say. It's a command prompt application without a graphical user interface. It's not, how to say, good for everybody, but if you are some nerd, let's say, and like to program, then this could be your choice. However, it requires some knowledge of programming in Python. This is a must really to make full use of this uncertainty calculator. Python nowadays has become a standard in software development, so there are many colleagues around the world which already know how to program in Python. I personally not, but if you are interested in that, so why not? You can give it a chance. The second or the fourth, to be honest, the others were second and third were demo versions. For this reason, I concentrate now on the MU kit, Measurement Uncertainty Kit. This software was developed to estimate uncertainties, especially for chemical, biological, and life science laboratories. So it is not just, how to say, to be used simply for physical uncertainty calculations. And there is some experience I found on the net, on the internet, that it is hard to be installed. So it takes some efforts really to get this software running. If you're interested in uncertainties for chemical stuff, biological things, and so on, then this could be your choice. But for the beginner, I think it's no good. Then there is a NIST, the NIST uncertainty machine. This software is based on the statistics software R, which is nowadays or has become really a standard, as also for many students, for many universities. This R, it's also free of charge. This software, you have to install it first, and then you have this add-on according to the GAM from the NIST. Also, Monte Carlo simulations are feasible. I think that's quite nice. If you have the patience also to install this statistics software first and then to deal with the installation, then could be quite good, could be your choice. I personally didn't try it because I didn't have the time also to install this statistics software. So here you can see some example. It shows the results and also some graphs about the probability densities. So I think it's simple but good and easy to use. Some people say after successful installation of this R software, yeah, you could give it a try. Then there is this Hewlett-Packard Uncal 3.2. That is, as they say, a simple uncertainty calculator. And I would say that it's unfortunately not easy to use and not so easy to learn. this is the only freeware I found which has really some kind of graphical user interface similar to the commercial software packages which are available. But I installed it by myself. It was fine, was okay. And I tried to do some simple things, but I failed somehow. I was not able really to implement one problem into the software and to specify the numbers. I think maybe there is really some time necessary to do this. I think this maybe is good. It's a good software, but not easy to handle. That's really no good, but maybe the only one which gives you really some graphical user interface. So it was originally produced for Windows 2000, so it's quite old. Plenty of functions, but if you really want to start, if you have, for example, no money, no budget, and you want to start some uncertainty calculations and not using Excel or something like this, then this could be an option, really. But then you need some time to, to get experience with this software. Unfortunately, it's not so easy. Also, if some people said, well, it's easy, but for me personally, it was not. Then already I explained the uncertainty sidekick software, which also guides you through the process. In principle, this is nice, also the freeware, but there is one big disadvantage, and it took me, unfortunately, several hours to find out. So it's a great user interface. It's nice. It's good. It's easy to use. But there is one exception for the freeware, and that's really bad. It doesn't allow you to calculate the measurement uncertainty for so-called multivariate measurements. So it means as soon as you have one quantity which depends on at least two variables, you are not able to deal with that with this freeware. You are only able to analyze some simple uncertainties from direct observations. If you have taken, for example, 15 or 20 measurements for one quantity, you can type in, you get the mean value, standard uncertainty, and so on, but not for complex problems as we all have. So in principle, you can start with the software to get some idea how it works, but that really to be able to work with this, you need the commercial version to pay at least $295. So I think with the free version, in principle, you cannot do very much. Unfortunately, that's very restricted. Then there is a NPL measurement uncertainty software, and comparable to the NIST uncertainty machine, it also requires some statistical software. It needs, in this case, it needs MATLAB's component runtime library, which are free of charge. That's fine, but also that's not so easy to be installed. I tried and I failed, I have to admit. I think it might be a very nice software, also allows Monte Carlo calculations and so on, but I was too stupid to install it. But I guess you all are experts and you can do that, and you will have so much fun with this software package. Okay. So my personal conclusions: for beginners and also professionals, I would recommend the three software packages, which also easily guide you through the process, which gives you a good user interface where you can type in easily everything. You don't have to think about the program itself. You can concentrate on your physics, on your measurement uncertainties. And I think if you have some little budget or some budget, then you should try one of those softwares. All the other options, commercial options, I also would recommend for professionals or specialists, but it depends what you need. And for the freeware, I would recommend eventually the Hewlett-Packard software, but it needs some time. You need some time really to understand how it works and where you have to type in what. It's unfortunately, it's not so easy like as a commercial software packages. But I think you can, if you really want to calculate some measurement uncertainties, then there is software available. You have a choice, which is also very good. And even you can give it a try also with the demo versions, with this Hewlett-Packard software, that you are not restricted to use Microsoft Excel, for example. So that's quite good. So that was it. It was my presentation. And as I mentioned in the beginning, you can, we will put this presentation on the comet.net together with some other files, and then you can download it, and then you have everything what you wanted to have. Okay, thank you. And I give back to Yuri now, and then we can come back also to questions and answers, hopefully.
Спасибо, Питер. Я так понимаю, что Питер меня не слышит. Я понял. Okay, thank you, Peter. Do you hear me? No?
Yes, now I hear you. It's really for some seconds I hear you, and then you are some seconds again gone. That always switches. I don't know why.
Okay, we will show on the screen the few questions.
Thank you. Thank you very much.
I will show my screen.
No.
Okay. In the document on the use of uncertainty estimation for conformity assessment purposes, there's a method called the guard strip method, which is widely used not only in metrology, but also in industrial practice. The method is to shift the MPE by uncertainty multiplied by 3. This approach allows us to abstract from the risks of measuring instruments false acceptance during calibration and to simplify the calibration procedure itself, practically without changing its essence in the traditional approach. Yes, I think I'm not 100% sure. I personally, I didn't read anything about this guard strip method, but I guess what it means is that you take a higher coverage factor, or maybe of 3, that in principle you take into consideration a larger amount of the probability density function, that you have more, that you lower the risk, I guess I would say. But to be honest, I cannot tell you anything about this guard strip method. So that's, I didn't read anything about this, unfortunately.
Maybe guard band method, Peter, no? Okay, the second question is from Alexander Danilov.
Okay, the question is, how should risks be evaluated in conformity assessment in those practical cases where the measurement results are obtained between the points of the measuring range at which the measuring instrument was calibrated? I have to understand this question. between the points of the measuring range at which the measuring instrument was calibrated. So, okay, I just turn it around. So it means the measuring instrument under test was calibrated within the range where of the maximum permissible errors, I guess. And then, of course, if it is calibrated that way, then there is a very high probability that it won't fail, that the indication will be within this instrument, within the maximum permissible error interval. And I think I would, in principle, take the same approach as for all the other cases, because usually I don't know how the instrument was calibrated, which standards were used, and there could be some deviations, and I would just do it conventionally. I would not take care on those calibrations. And even you could maybe try it, for example, if you do verification of an instrument, then usually you don't do the testing or the verification not only just at one point of the measuring range, but you do it at several points. Then you can take also another standard and just to take a measurement somewhere where it wasn't calibrated before. I think that's okay. I wouldn't care on that.
Okay, thank you. There is no other questions.
Are there more questions?
No.
Okay.
Окей. Коллеги, мы подошли, насколько я понимаю, к завершению и вопросов, и, собственно говоря, основной темы вебинара. К сожалению, видите, технические проблемы. Господин Петр не слышит меня, и мы попытаемся еще каким-то образом, может, оставшиеся вопросы озвучить. Но что бы я хотел сказать? Несомненно, вот, со своей точки зрения оценю то, что это практический подход к достаточно сложному документу. Это несомненно. И я бы очень хотел сказать, выразить благодарность, во-первых, нашим переводчикам. Это непростой труд, они много поработали сегодня. Ну и, конечно же, секретариату. Наде лично, моим коллегам, всем, кто обеспечивал каналы связи и всем, кто поучаствовал, несомненно. Благодарим за терпение. Возникают все-таки какие-то технические трудности. Слишком много каналов одновременно приходится задействовать. Все работают с разных точек мира. И, ну, несомненно, интернет не всегда выдерживает, тем более, что подключений у нас колоссальное количество, благо мы сумели некоторые подключения сконцентрировать. И еще раз благодарю, очень рад был всех видеть в участниках, кто поучаствовал. Коллегам из технического комитета говорю до завтра. Мы начинаем завтра наше заседание, и если есть еще дополнительные какие-то предложения, замечания, пожалуйста, прошу выступить. Надя, может, ты что-то хочешь добавить?
Юрий, спасибо. Нет, ты уже все сказал. Действительно, у нас получился очень интересный и полезный семинар. Вот я вижу, что Николай Дамыч хочет выступить. Мы сейчас обязательно предоставим его слово. Я благодарна всем участникам, которые остались с нами до конца нашего вебинара. И надеемся, что он действительно был полезен для всех вас. И, как обычно в этих случаях говорится, мы ждем вас на наших новых мероприятиях. Спасибо всем.
Включила звук.
Николай Адамович, пожалуйста, здравствуйте.
Можно я скажу пару слов?
Питер, не прошло и года, как эта прекрасная идея притворилась в твоем докладе. Спасибо большое, что взялся за эту тяжелую работу и замечательно, доходчиво и понятно рассказал нам про нее. Успехов тебе в будущей работе.
Самое интересное, что Питер, к сожалению, не слышит, насколько я понимаю, все равно перевода.
Это надо на русском написать, они переведут.
Мы сейчас это все напишем.
А на английском он поймет или нет?
Да.
Питер,
Да.
thank you very much for your perfect report about so no simple matter.
Вообще ничего не слышу. А еще раз, Николай Адамович, попробуйте на английском.
Оля, выключи перевод у себя.
Я выключила вообще все. Попробуйте еще раз, Николай Адамович.
Питер, не слышит. Питер, many thanks to you.
Я ничего не слышу.
Кажется мне, коллеги, что надо нам учить для зума еще и язык жестов. Это было бы неплохо. Ну, извините, вот это что-то с каналом. Мы сейчас попробуем написать Питеру в чате. Мы еще обсудим некоторые нюансы с нашими коллегами, потому что у нас впереди 2 тяжелых дня еще. Окей, спасибо.
Уважаемые коллеги, мы обязательно передадим все слова Питеру завтра. Надеюсь, у нас не будет проблем с коммуникацией. И все ваши слова мы обязательно ему передадим лично.
Хорошо.
Спасибо вам большое и просим еще раз прощения за некоторые технические накладки.
Надя, я здесь все выключаю, да?
Да.
Okay.
Питер. Собственно говоря, это на той стороне, потому что меня, насколько я понимаю, слышно нормально абсолютно.
Я думаю, что это у него с его подключением проблема. Сейчас еще обсудим это, Юрий.
Да, окей. Надь, нам надо YouTube стрим остановить.
Угу. Сейчас я передам права.
Игорь, давай напишем на экране. О, Питер отключился совсем. Да?